after calculating Qt upon AP, which came out as 198.39, we are going to calculate UT, which is nothing but Qt upon TPM minus TA. Qt upon AP is 198.39, TPM we calculated as 347.6, atmospheric temperature is 28 or 298 Kelvin. So, for this if you calculate, UT is coming around 3.99 watt per meter squared Kelvin. And then UB, for UB you would require the thermal conductivity of the insulation material and bottom insulation thickness, that is given here Ki and bottom insulation thickness. Ki is 0.04, bottom insulation thickness is 5 centimeter or 0.05 meter, which is coming around 1.25 watt per meter square. So, the assumption is 10% of UB can be taken as US. So, 0.125 watt per meter square. After calculating everything, heat loss coefficient UL is UT 3.99 plus 1.25, that is UB, US is 0.125. If you calculate, it is coming around 5.3741 watt per meter squared Kelvin. So, what we assumed? We assumed UL to be 4 watt per meter square and calculated TPM, that is plate mean temperature, and after that to calculate, because the plate and cover system is filled with air, to calculate all the losses, then we assumed collector temperature as 305.6 Kelvin and then proceeded the calculation. We are getting now UL as 4 watt per meter square. So, that seems to be not coinciding, because the difference between calculated value and guessed value is so much, but still we will try to see how much we are getting as a outlet temperature and instantaneous efficiency. After that we will go back and recalculate in the sense we will assume some other initial guess for UL and TC and then proceed the calculation and see what is the final efficiency we are getting, right. So, if we calculate, then if we know UL, QU is nothing but MCP T out minus T in. So, this T out is nothing but QU upon M dot Cp. So, what is QU? 1054 watt, mass flow rate is 75 kg per hour and Cp is 4180 kilojoules per kg degree centigrade. So, here we were given Cp, joules per kg Kelvin, and then this is Cp, mass is 75 kg per hour, right. So, this is in watts. So, we would require this is kg per hour. So, we need to divide it by 3600 to get into watts get cancel and then Kelvin, it will T out would come in Kelvin. So, basically 1054 upon 75 into 4180 upon 3600. So, which is coming around 340 Kelvin. So, if you see what is the wrong here, the prediction of whatever we are getting T outlet temperature as 340 is wrong. Why it is? Because the 1054 QU what we calculated is based on UL 4, right. But whatever we got through the calculation is 5.3, but still we are learning the method and we will recorrect or re-guess this UL value and try to predict correct outlet temperature. Once outlet temperature is known, then for T in how much we have given 55 degree, which is nothing but fluid inlet temperature. Here if you see 55 degree. So, 55 degree plus 273, which is nothing but 328 Kelvin. So, for 328 Kelvin, how much outlet temperature we got is 340 Kelvin. And for instantaneous efficiency, again QU 1054 upon IT we calculated as 950, and AC is, the details are given here in the problem, collector area, right. Length of the collector and width of the collector is given. It is not a plate area, it is a collector area, it is a gross area. So, 2.08 into 1.07, 2.08 into 1.07. So, if you calculate eta I is coming around 0.49 percentage or 49 percentage. So, this is the way you calculate the instantaneous efficiency and outlet temperature of the fluid for the given data, whatever we discussed in the problem. So, if you want to check correct values, so here I have given. So, here UL is taken as 5.3 watt per meter square Kelvin and TC is taken as 305.21 Kelvin. For this, what are all the parameters we are getting and what the values I am giving, you can take it as a home task. And for rest of the data, whatever data given in the problem is same, but we assumed UL as 4 and proceeded the calculation, and TC we assumed as 305.6, but here we are re-guessing the UL value as 5.3 watt per meter square Kelvin and TC as 305.21 Kelvin. We will check whether UL is coming same or not. So, I am just giving you the calculated parameters. You can do it as a home task and let us know parameters and then values. So, the M is 10.0763, M W minus D naught upon 2, which is 0.5003, phi is 0.9242, F dash is 0.8831, M dot Cp upon UL AP is 8.3831, FR is 0.8381, QU is 947.8 watts, QL is 494.6 watts, TPM is 345.62, TC is, this is cover temperature 325.41, then T average, which is nothing but TP plus TC upon 2, which is nothing but 325.41. Then we have beta T, which is nothing but 1 upon T average, which is nothing but 0.0031. Then thermal conductivity of air at average temperature is 0.0282, nu is 1.822 into 10 to the power of minus 5, alpha is 2.5979 into 10 to the power of minus 5, Rayleigh number is 4.01 10 to the power of 4. Then we supposed to calculate RAL cos beta, which is nothing but 3.479 10 to the power of 4. Nusselt number calculated is 3.1936. HW is 16.48. HPC is 3.6. QT upon AP for plate to collector system is 189.07. QT upon AP to cover to surroundings is 189.09. QT upon AP average value is nothing but 189.08. and UT is coming around 3.97, UB is coming around 1.25, US is 0.1250, UL is 5.3457, T outlet temperature is 338.88 and instantaneous efficiency is 0.44, right. So, if you check your check for TC is coming correctly and the guessed value is 5.3 watt per meter squared Kelvin, the calculated value is 5.34. So, pretty much this is converging this particular value of UL and TC for the given data, right. So, now as I said earlier, to guess correctly you might do it twice or thrice, or if you have experience, and pretty much for this simple liquid flat plate collector mostly the plate mean temperature would be around 350 Kelvin, right. Last time we got 346, but how much 345, right. But the thing is, why we supposed to balance this exactly here is that is where we learnt certain thermodynamics laws, right. So, you cannot, for example, the heat loss given from plate to cover system should be high than cover to surroundings, right. So, you should be having higher temperature in the cover and lower temperature in the surroundings, right. So, if the reverse happens, for example, if your absorber plate temperature is less than that of the fluid inlet temperature, then instead of getting heat, it will give away its heat, fluid will lose its heat. So, these are all the places you supposed to apply the thermodynamics laws and check whether you are doing it correctly. So, pretty much, and also this UL, right, why we are calculating UL is to find out UT, that is top loss coefficient. But for there also you have many correlations which predicts the top loss coefficient. If that is the case, UB US is straightforward. You supposed to calculate the area and then thickness and thermal conductivity values are available. So, with that also one can calculate. For UT also, if there are correlations available, then you can directly use that as well. So, here we have discussed all the possibilities and how to do the analysis in depth. And one more thing I would like to emphasize here is for the Indian Standard Time of 10.43, the value we have taken, that IB as 725 and ID as 230, that is like for very hottest environment. Okay. So, normally that may not happen around 12 noon. You might get this high radiation of watt per meter square, this also we discussed. So, here we have taken this value just to show you the performance analysis. Even for that high IB and ID, how much we got, instantaneous efficiency is 0.44 only. So, here as I said earlier, you can plug and play, right. Instead of taking 725 and 230, if we take 547 watt per meter squared and 210 watt per meter squared, this is pretty much okay for 11 AM of Indian Standard, any decent hotter cities. So, for that the eta I is coming around. So, this is separate problem. For that the IT is 751 watt and S is 582 watts and instantaneous efficiency is 0.42. Alright, everything is lower than that. And one more thing also here to mention, we have taken epsilon P as 0.14, that is nothing but the emissivity of the plate, which is 0.14. So, this value also it is like higher, right, for any good absorptive surfaces, because the plate should absorb the solar radiation. And for this, instead of 0.14, if you assume 0.08, that is supposed to be called as ideal surface. Ideally it should be 0, right. The emissivity we have taken 0.08, then what you would get efficiency as 0.43. So, for 0.43 this values I kept, right. for IB of 547 watt per meter squared, ID of 210 watt per meter squared, IT of 751, S of 582. If we just change the plate emissivity value as 0.08 instead of 0.14, you would arrive with 43% efficiency. So, like this you can change the given data and see how your efficiency is affected by many other parameters. By here it is shown us like we learnt in the first lecture itself, solar radiation is nothing but a short wave radiation, and from there radio waves as well as visible light would reach the earth's surface, and for UV and IR it is reaching the earth's surface in an attenuated form. And if you see gamma X-rays, they will not reach the atmosphere. So, the earth is having a temperature less than that of the sun and it re-radiates, right, basically. So, when it re-radiates as a long wave radiation, right. So, the plate material, if it re-radiates more or if it emits more, then that is not of much useful. So, here there are many research groups working on this particular surface modification itself, right, how to get higher absorptivity and low emissivity. And also if you remember, solar radiation reaches us short wave. So, radio waves plus visible light reaches the earth's surface, and IR and UV in attenuated form. And if you see gamma X and all, they will be filtered by the atmosphere itself, right. When it reaches the earth's surface, it radiates back as a long wave radiation, because earth does not have that much energy to radiate as a short wave. So, here if you see, there is a research article on which it said that the solar radiation, the wavelength range is less than 4 micrometer. This we have discussed in lecture 1 as well. You can refer it. But when it re-radiates greater than 4 micrometer, especially maximum at around 8.3 micrometer. So, there is a article in that. So, for this purpose normally the ideal surface, what I was talking about is ideal surface of the plate, right. So, for this the alpha lambda, which is equivalent to epsilon lambda, which is kept at around 1 for lambda less than 4 micrometer, that means solar radiation. But if alpha lambda epsilon lambda is 0 for all lambda greater than 4 micrometer. So, this is ideal, but how to get in reality, because we already know there is no perfect black body, right. So, how to get them in reality? There are certain research groups working on that materials research to get this particular ideal surface, but we are not getting into that. So, what I wanted to make is, so this particular radiation, for that emissivity should be 1, and for all long wave radiation the emissivity is going to be around 0. So, if you see, this is lambda, so this is around 4 and this is higher value of 4. So, this is nothing but emissivity data. So, here that is what I told you, instead of emissivity of the flat plate as 0.14, you can take it as 0.08 and we calculated as 0.43 for this given data. The same way you can work around, for example, this data we have taken as one glass cover system. So, if you put more or 2 above than that, whether the losses, because the cover system, its function is to protect the plate from environment and also you should allow the solar radiation to absorb on the absorber plate, and it should emit less, right. It should prevent the convection and radiation losses. So, in that way, so how many covers, glass covers would be required. So, that analysis you can make, and change the fluid temperature, fluid inlet temperature, and check whether if efficiency is increasing or decreasing. And as I said earlier, instead of instantaneous efficiency, you can also calculate in terms of daily or hourly efficiency, because radiation is slow phase. So, that is all, and here are the references. The basic design of problem is taken from Sugatme and Nayak for all collector details, and Bechberg, Cotton and Edwards, Bechberg et al. Is used to calculate HPC value, the Nusselt number correlations whatever we used in this lecture, and Test et al. This is used to calculate HW correlation. And then Hallman, you can use it to get K thermal conductivity, nu and alpha values for various temperatures. I expect you to do this home task for different values and check further, because we are limited with lectures. So, we may not be able to do all the problems here. So, I expect you to analyze based on whatever we discussed. Thank you.